Hello everybody, my name is Mohit Deshpande, and in this video I want to discuss color models, and it's going to be kind of our first image processing topic here, color models. And so we've discussed the mathematical foundation of images, which are matrices, so now let's talk about images specifically, and a good thing to talk about with images when we're starting out is color. And so a color model is actually a way, it's a mathematical system of describing color. And this might sound kind of confusing, and actually let me just rewrite that word. It's kind of messy here. Describing color. And so you might have, this might sound kind of confusing, but there are some things that you might have heard. For example, you might have heard of RGB. So let me actually draw that. R, G for green, or is red, and then B, blue. You might have heard of this thing called RGB, and that's actually an example of a color model. We use 3 values to describe any particular color, and with RGB we take different amounts of red, green, and blue light to be able to produce any color you can think of. So this is kind of an example of a color model, and there are more color models, and I'll get to just one more in a bit later on in this video. But that's just what a color model is. It's just a simple mathematical way of describing, any kind of color. Now, while color models are great mathematically, we're going to eventually be programming this stuff. So instead, there's a small but subtle differentiation between a color model and a color space. And a color space is a more concrete, it's a more concrete way of implementing this color model here. And what I mean by that is just knowing RGB just isn't enough when we're discussing and when we're actually going to be programming these images. That's not enough information. So we need to know other things like what are the possible ranges of values, or how is RGB arranged in some computer science construct? How do these things work like that? Those are kind of the things that we need to know programmatically. Mathematically, that's just implementation detail, but we have to discuss both since we're going to be programming this as well. So things like things like color space address like ranges. What are the ranges of R, G, and B? And for OpenCV, it turns out that for R, G, and B, this goes from 0 to 255, which, if you remember anything about sequences, this is actually 256 numbers, which is 1 byte. So each of these takes up 1 byte. Goes from 0 to 255 inclusive, so we include 0 and 255. And just to put a dot here, 0 is black and 255 is white here when we're dealing with a single value here. But with RGB, we actually have 3 values, so that means that we kind of can mix red, green, and blue light to produce all different kinds of colors. And this is an example of this RGB color space. And one important thing to remember about this, and I'm going to write it in purple, I guess, since we've already used red, is that there's no kind of absolute color. And what I mean by that is it all depends on what color model you're using. The values of this change. Let me actually underline this so that it's very clear. There's no absolutes when we're dealing with color, because it changes based off of the color model. For example, let me give an example here. So white for RGB, white, oops, that's RGD, I meant RGB. For RGB, white is 255, and 255. So for each of these values, this is a tuple. The red value is 255, which is the max. the green value is 255, which is the max, and then the blue value is also 255, which is max. And this is white, the color white, pure white. So these are the particular values in the color space that produce a color white. Now that's great and all, but suppose we were using a different color model and consequently a different color space. And let's just look at another one. I'm not going to discuss it at all, but I just want to use this to illustrate the point. And this is hue HSV, which is hue saturation and value. And this also has 3 values to represent any color, but these values that it represents white are different. And in fact, for HSV to get pure white, it's actually 0, the tuple is 0, 0, 100. So you see that it's not the case that white is only 255, 255, 255 for all color models. We see that it changes based on the color model. So this is also white. So hopefully this illustrates the point. I'm not going to talk too much about HSV since most commonly we're going to be sticking with RGB. But hopefully this illustrates the point that there's no such thing as an absolute color, because it's all relative to what color model you're using. If you're using RGB or HSV or CMYK or whatever, it all depends on what color model you're using. And in fact, these values even change as well. So hue, saturation, and value, these are actually different. So RGB, we know that this goes from 0 to 255. I should put this specifically for RGB ranges, 255. But for HSV, it's actually completely different. So H goes from 0 to 360, and then saturation and value actually goes up to 100. So those are even completely different ranges. So it really brings the point home that it's all about the color model that you're using. Everything's relative to that. But anyway, we're not going to talk too much about hue, saturation, and value, because we're actually going to be sticking with RGB and Greyscale. And so let me just mention something about Greyscale here. Actually, Greyscale. So first of all, what is Greyscale? It's just different shades of... It's just a way that we can represent different kinds of gray. It's just a range, basically, a range of different kinds of gray. And it's different than RGB because RGB uses 3 values, but this has just 1 value to represent colors. And because of that, it's also more restrictive than RGB because you can't really, there's no color with Greyscale. It's just a gray image. It's like you take the color image, it's just like you take the color out of a color image, and it's just all different kinds of gray, where the darkest, this is where Greyscale actually comes in, as from 0 to 55, a single value here, and this also applies to Greyscale, where 0 is black and 255 is white, and then anything in between is some kind of gray. And so there are these 2 different color models, and as it turns out, there's ways that we can convert in between color models. So for example, if I wanted to convert from RGB to Greyscale, so if I wanted to do RGB to Greyscale, well, a simple way of doing that, a very intuitive way, is just taking the red value plus the green value plus the blue value and dividing by 3. So we kind of like average the red, green, and blue value, and that produces a single value, and that's how we interpret that as being Greyscale, as being a shade of gray between black, which is 0, and pure white. Now, there are more sophisticated ways than averaging. Some people like to actually assign weights to each one of these, so it's kind of like a weighted sum, but that's more complicated because then that starts to get into the physics of these wavelengths, and that's just way beyond the scope of what we're trying to do with basic image processing and color models. But anyway, that's kind of, and this is kind of describing what color models are, in Greyscale and RGB are actually the 2 most common ones that we'll be using. And you see that we can convert from RGB to Greyscale, but converting from Greyscale to RGB is not really easy to do. And that's because when we initially convert to Greyscale, we actually lose information. So this R plus G plus B, because it's a sum, there's no way to really recover which portions of RGB were actually being used. However, this isn't really much of a problem because some of the image processing tasks that we're going to see later on actually don't really care about color, and in fact, they'll fail if you try to give it a color image. They'll tell you to convert it to grayscale because we don't need color information. So usually when we're dealing with kind of the more advanced image processing techniques, we'll take an input image and convert it to grayscale anyway because color information for a lot of image processing tasks actually is not that useful to know. And so now that we've discussed color models, we can actually get into the next video. We'll talk a little bit about some of, an actual image processing property, and then we'll see how we can use matrices. Incorporate matrices to see how we can represent it mathematically, and we'll be using color models later on as well. So just to recap what we did in this video, we discussed the difference between color models and color spaces, where color models are more mathematical and color spaces are a bit more concrete. We discussed the RGB color model and the grayscale color model and how we can convert from RGB to grayscale. I also tried to make the very important point that there's no absolute color. It just doesn't exist. It's all relative to the color model. And I kind of gave the example here with RGB and another popular color model, hue, saturation, value, in the sense that the pure white is actually different in these two color models. So there's no absolute value that represents pure white. It's all dependent on the color model. So that's kind of the things that I talked about in this video. And RGB and grayscale are actually the two most common ones that you will be dealing with anyway, and we'll get to them very soon. And in the next video, we're going to discuss some more image processing, particularly two of the most simplest image processing properties called brightness and contrast.